So, good morning, my dear students. My name is Dr. KCH Apparao, working as an associate professor in mechanical department, Institute of Aeronautical Engineering, Hyderabad. Okay, in previous classes, we discussed the rate of heat transfer through two types of the fins. One is the long fin, another one the insulated fin or short fin. We derived the formulas also. Just for the long fins, we derived the formula Q is equal to under root of HPKA into theta naught. Similarly, we derived the formula rate of heat transfer for the insulated end. So same under root of HPKA theta naught into tan H ml. So we derived that one. Now we'll see the third fin. So third type of the fin. So that is the fin with convection of the end. Fin with the convection of the end. So here we'll see the condition. So in three pins, basic boundary condition means boundary condition 1 is same. That is, at x is equal to 0. So temperature T is equal to T naught or theta is equal to theta naught. So this is common for three pins. But second boundary condition will be changed. So in the first pin or the long pin, it means at x is equal to x tends to infinity. So temperature T will be T infinity, ambient temperature. That is the second boundary condition of the long pin. So in second pin, insulated end or short pin, so that is the d theta by dx is equal to 0. That is the condition. Based upon this condition, second boundary condition will be applied. So in third one, we will see the boundary conditions. So this is the case we will see that one. Okay, so this is the case of finite fin. This is the finite fin where the heat conducted to the end is convected away to the surrounding fluids. It means so rate of heat transfer by conduction is equal to rate of heat transfer by convection. So you know that the formulas minus Ka d theta by dx with respect to conduction is equal to so HA theta naught with respect to convection. So this principle you have to apply here. So based upon this, the second boundary condition will be changed. Okay. So the mathematical formula of this formula, just for this one we will see this one. Here we will see the boundary conditions. So first boundary condition, you know that same boundary condition for the three fins, long fin, short fin and convection of the end. So at x is equal to 0, so you know that theta is equal to t naught, nothing but t naught minus t infinity. Okay, so this is the boundary condition 1. That secondary boundary condition, it is a finite fin. It means it has some length of the pin. So if you take that x is equal to L length, then the condition is equal to so minus Ka dt or d theta by dx. We can write like this one is equal to HA theta or theta naught. So if you apply the x is equal to L, that is the theta naught. Okay. So here area same will be cancelled. Then you can rewrite like this one K dt by dx plus h theta is equal to 0. So this one. So this is the just like second boundary condition. This is the first boundary condition. This one is the second boundary condition. Then you have to apply the boundary conditions to general equation. Then you will get the constant values C1 and C2 and substitute the C1 and C2 in general equation. Then you will get the temperature equation. By using the temperature equation, by integrating the temperature equation, you will get the rate of heat transfer in the particular fin. So this is the same process what you have applied in previous two fins also. Now we'll see that we'll derive the rate of heat transfer in the fin with convection at the end. We'll see. So you know that the first boundary condition, at x is equal to 0, theta is equal to theta naught. Okay, if you apply this first boundary condition in general equation, we know the general equation. So that is nothing but theta is equal to c1 e to the power of minus mx plus c2 e to the power of mx. Okay. So theta is nothing but t minus t infinity. You can write like this one. So t minus t infinity. If you apply the first boundary condition, what is the first boundary condition? At x is equal to 0, then theta is equal to theta naught. Okay, so then theta will be theta naught c1 e to the power of minus m into 0 in place of x plus c2 e to the power of mx m into 0. So e to the power of 0, that is the value of 1. So theta naught is equal to c1 plus c2. This is the equation 1. Here we can observe. Okay. So this is the equation 1 by the first boundary condition. Now we'll apply the second boundary condition. So that is at x is equal to L, we have to apply this one. K d theta by dx plus h theta is equal to 0. We have to apply this one. Now we'll see that one. So here you can observe. So you know that this one, these are the same. Okay, this is the second boundary condition at x is equal to 0. So minus k dt d theta by dx is equal to ha d theta by d. So convection rate of heat transfer by conduction is equal to rate of heat transfer by convection. So here a cancel. So you know that the remaining formula will be like this one. So by using the first boundary condition, we will get that theta naught is equal to c1 plus c2. So at second boundary condition, at x is equal to 0. At x is equal to 0. So apply this principle. So you know that you can rewrite like this one. It means k d theta by dx is equal to minus h theta. Okay. So or d theta. So then d theta by dx is equal to minus h by k theta. Okay. So it means, so you know the theta value. So theta is nothing but so derivative of derivative with respect to x dx. So theta value is equal to, you know that c1 e to the power of minus mx plus c2 e to the power of mx is equal to minus h by m h by k here into theta naught. Theta naught is nothing but not theta. So theta is equal to general equation, that is the c1 e to the power of minus mx plus c2 e to the power of mx. So here just like we have to derivative this one with respect to x, then we have to substitute the value of x. X is equal to L, then we will get this one. We will see here also. So c1 e to the power of minus mx, derivative of the e to the power of minus mx means we will get minus mx. Here we will get minus mx. Just I am writing here c minus m, same term c1 e to the power of minus mx. So in x place you can write the L value. So okay, plus e to the power of mx. E to the power of mx means so derivative of e to the power of mx means m will be come before, that is the m into c2 e to the power of ml. Okay, so e is equal to minus h by k into, so c1 here also you have to substitute the value of x. X value is equal to L. So c1 e to the power of minus ml plus c2 e to the power of ml. Okay, this is the, we will get this one. So in this both cases, m is the common term. So you can take the common and you can send it here. Then minus h by mk. So you will get this total term here. Okay. So after derivation and the substitution of x value is L, then we will get, so this step. So minus C1 e to the power of minus ml plus C2 e to the power of ml is equal to minus h by mk C1 e to the power of minus ml plus e to the power of ml. So same term here we will see. So you know that generally, so first by the first boundary condition we got that C1 plus C2 is equal to theta naught. Okay, then you can rewrite like this one, C2 is equal to theta naught minus C1. So substitute this value in equation 1. What was here? This is the equation 2. You can take that one. So this is the equation 1. Okay, so you can substitute the C2 value in equation 2. So we got this equation 2. Okay, by applying the, by derivating the general equation, apply the x value. Okay. Okay, so minus C1 e to the power of minus ml plus, in the place of C2 you can write to theta naught minus C1, theta naught minus C1 e to the power of ml. Here also minus mk C1 into e to the power of minus ml. In the place of C2 you have to write this one, theta naught minus C1 e to the power of ml. So then solve this one. Here just if you solve this one you will get this term. Just I am repeating this one, so listen carefully. Minus C1 e to the power of minus ml plus theta naught, here theta naught into e to the power of ml. So theta naught into e to the power of ml minus, here minus is there, C1 into e to the power of ml, C1 into e to the power of ml. So that is the first term is equal to, so here also you can multiply minus h by mk with the total terms. So it means so C1, so first of all minus h by mk C1 e to the power of minus ml plus, so minus h by mk into theta naught. Okay, so minus here is there, here also minus, minus and minus plus, so h by mk into C1 e to the power of ml. Okay, here C1 terms, you can collect all the C1 terms in one side, remaining theta terms in another side. So if you take the common C1, then you will get this total term. So C1 into e to the power of ml. So here C1 into e to the power of ml. So this one. So C1 into e to the power of ml plus e to the power of minus ml plus h by mk into e to the power of ml minus e to the power of ml. So we'll get the total term. So theta naught e to the power of ml is the common term. Here we'll get 1 plus h by mk. So theta naught e to the power of ml. So here is the common term. Just you can take theta naught e to the power of ml. Okay, you can take common, so theta naught e to the power of ml, then you will get the 1 plus h by mk. So this is the term. Okay, then C1 is equal to, so this is the value, C1 is equal to, so theta naught e to the power of ml into 1 plus h by mk by the total term. This is the total term. Okay, so you know that C1 is equal to, C2 is equal to C1 minus theta naught. So in which you got the value of C1, then you can find the value of C2 also. If you substitute the C1 value, what is the C1 value? So this total term minus theta naught. Okay, so if you solve this one, automatically you will get the C2 value. That C2 value is will be like this one. C2 value is equal to, so theta naught e to the power of minus ml into 1 minus h by mk, here 1 plus, here minus. Okay, so h by mk. So remaining denominator term is same for this one, for the C1 and C2. Okay, if you solve this one, you will get same term. So this is the C1 and C2 values. Okay, so then you can substitute the C1 and C2 values in general equation. Then we'll get the temperature formula. Okay, so substitute the C1 and C2 values in general equation. The general equation, theta is equal to C1 e to the power of minus mx plus C2 e to the power of mx. Okay, so substitute the value just like so. Just theta is equal to C1 is equal to that C1. So C1 is equal to theta naught e to the power of ml. Theta naught e to the power of ml into 1 plus h by mk. 1 plus h by mk. Okay, into e to the power of minus mx. So this is the term divided by same terms. What is the term? E to the power of ml plus e to the power of minus ml. E to the power of ml plus e to the power of minus ml plus h by mk. H by mk e to the power of ml minus e to the power of minus m. E to the power of ml minus e to the power of minus m. So this is the term. So for this one plus C2. So what is the C2 value? C2 value is equal to theta naught into e to the power of minus ml into 1 minus h by mk into e to the power of mx into e to the power of mx. So divided by same term here also same term. Okay. Okay, so if you solve this one just like so, finally you will get to this one. Here theta naught is the common term, so you can take here then theta by theta naught. So then if you solve this one, it means so e to the power of m into l into e to the power of minus mx. Okay, so plus e to the power of h by mk into e to the power of ml into e to the power of minus mx. Okay, so here just if you solve this one, so you can rewrite like this one. It is the e to the power of m into l minus x here. So plus h by mk into e to the power of m into l minus x here. So here just like if you solve that one, you will get the formulas and the formulas that hyperbolic functions, that is the hyperbolic function is equal to so e to the power of x plus e to the power of minus x by 2. So plus that shows the so cos h m mx cos h is equal to cos h x. Okay, so e to the power of x minus e to the power of minus x by 2, that is the sin h x. So apply this one, then we'll get this formula. Okay, so cos h m into l minus x plus h by ml into sin h m into l minus x. So by cos h ml plus h by mk into sin h ml. So this is the formula, you got that one. Okay, so now we'll see that this is the temperature formula. So what is the temperature formula? So this is the temperature formula. So theta by theta naught is nothing but T minus T infinity. So this is theta by theta naught is equal to T minus T infinity by theta naught minus T infinity. So this is the temperature formula. By using this temperature formula, you will get the temperature at any particular distance. Just like if the x value is given, then you can find out the temperature. The temperature is given, you can find out the a particular distance x value. So this is the formula. So by using this temperature equation, we can find out the rate of heat transfer. Okay, so for this one, you know that Fourier's law for the conduction. So Q is equal to minus Ka into dt by dx or d theta by dx, because theta is equal to t minus t infinity. Derivative of theta with respect to x is equal to dt by dx. T infinity is the ambient temperature, that is the constant, you can consider that one. So then Fourier's law is equal to q is equal to minus ka d theta by dx, d theta by dx. So okay, uh, you know that here d theta is there, you can derivative with respect to x, then you will get the this value. Okay, here substituting d theta by dx. So d theta by dx, you can send this theta, d theta naught, so theta naught of. So next derivative of this one. So uh, cos h, so that is the minus cos h sin h m into L minus x with respect to x means you will get m derivative of that one. So minus here also, because uh, here also m is there. Okay. So h by m sin h m into L minus x. So with respect to minus x, you can get the m value. So minus m value. So here, so remaining is the terms. These are the constant cos h ml, because there is no x value. So then you can take the minus m common. So minus m common. So you'll get that one. The formula is will be like this one. Just okay. So minus m. So if you take the minus m, it means minus ka into minus m. Here you will get. Okay. So with respect to here also, uh, it means derivative of sin h ml will get the minus cos h ml. Will get, so here also minus. Next to, so remaining terms, minus and minus plus will be, so that will be plus. Okay. So then, so m is equal to, you know that m square is equal to hp by ka, then m is equal to under root of hp by ka. Okay, here already ka is there, so it means so ka into under root of hp by ka. So then, so here under root, here so no root, so you can so if it is cancelled, it will comes into under root. So then this value is equal to hp ka. So if you multiply with m into minus ka, so you will get this one. So theta naught is the common term you can take. So okay, if you take x is equal to 0, if x is equal to 0, this will be sin h ml. So here h by mk into, if you substitute x is equal to 0, so that is cos h eml divided by, so here same term cos h ml plus h by mk into sin h ml. In both terms, you can take the common cos h ml. So if you take the common terms cos h ml, so just I'm writing here. So sin h ml by cos h ml, if you take common, so plus h by mk divided by, here also if you take the cos h ml, so cos h ml by cos h ml, so that is the so 1 plus h by mk into, so sin h ml by, so cos h ml. So this is the value. So cos h ml, cos h ml will be cancelled. So then sin h ml by cos h ml means, so tan h ml minus, so this is the minus h by mk. So plus 1 plus h by mk into sin h ml by cos HML, that is the tan HML. So this is the formula. Finally, we got this formula. So theta is equal to under root of, so HPKA into theta naught into total term. So it means so tan HML minus H by MK H by MK by 1 plus H by MK into tan HML. So this is the just like formula. So finally, so this is the rate of heat transfer in the fin with convection of the end, not insulated, convection of the end. So these are the just formulas for the three types of the fins. This is the formula for the first fin, that is the long fin. So derived that one, Q is equal to under root HPKA theta naught. So this is the formula, rate of heat transfer in the insulated end fin. Insulated end fin. So under root of HPKA theta naught into tan HML. We derived this one also in previous class. So next, fin with the convection of the end. So that is the Q is equal to under root of HPK theta naught into tan HML minus H by MK plus 1 plus H by MK into tan HML. So this is the just derived this one. So Q is equal to, so this is the formula. So finally, the rate of heat transfer in the three types of fins, long fin, insulated fin, convection of the end fins are given here. Okay. So sometimes this type of derivations also will be asked in the examination, like so this is the one surface, this is the another surface, in between there is a fin. Okay, so the boundary condition at the first surface will be given BC1, and the boundary condition second surface BC2 will be given. So then the diameter will be given, length will be given, then derive the rate of heat transfer in the fin. Okay, if the boundary conditions are given, so then you can apply the boundary conditions in the general equation. You know the general equation that theta is equal to C1 e to the power of minus mx plus C2 e to the power of mx. So substitute these boundary conditions in general equation, then find the C1 and C2 values, then substitute these C1 and C2 values in general equation, then you will get the temperature equation theta by theta naught. It means T minus T infinity or something. If you get the temperature equation, then if you derive this one with respect to Fourier's law or based upon the conduction or based upon the convection, so then you will get the rate of heat transfer. So, okay, same what was just taught to find the rate of heat transfer in the previous slides, previous classes. Okay. So we can solve or we can derive the rate of heat transfer for the fins at a different boundary conditions. At a different boundary condition. So these are the formulas. So these derivations are very important to practice this one. Now we'll see the performance of the fin. Performance of the fin. So how to measure the performance? How to evaluate the performance? So this evaluation of the performance of the fin is achieved by just like by evaluating the fin effectiveness and fin efficiency. By using these methods, we can we can understand the performance of the fin. Okay. So if you want to evaluate the performance of this fin, you have to study about the fin effectiveness and fin efficiency or total efficiency. Okay. So here just like you. This is the base surface of the engine. So rectangular piece or pin is attached to the surfaces. The general concept. So this is the rate of heat transfer entering into the small elemental area. Rate of heat transfer leaving from the small elemental area. So this is the Q convection, rate of heat transfer through convection in the small elemental area. So this is the width and the thickness T. So the distance is equal to from here x is for the small elemental area. If you get the small elemental area, if you next integrate this one, you will get the rate of heat transfer for the total entire fin. So what was applied in the previous classes, you know that one. So now we'll see first of all efficiency of the fin. So it is represented by, okay, so we'll see efficiency of the fin. So you know that it is a ratio of heat dissipation by the fin to the heat dissipation takes place if the whole surface area of the fin is at the base temperature. So it means whole surface of the fin it at the base temperature means T naught. It means T naught minus T infinity. So it is maximum temperature difference, because temperature T naught is the, so engine surface temperature, T infinity is the atmospheric temperature. So the maximum temperature difference is the temperature difference is the just like maximum highest temperature minus lowest temperature. These are the, so the rate of heat transfer at this condition means maximum rate of heat transfer dissipation, maximum heat dissipation from that fin. So we can define like this one. So it is the ratio of actual heat transfer of the pin to maximum possible heat transfer of the pin. So maximum possible heat transfer will be occurred at the temperature difference is equal to T naught minus T infinity. It means so if you assume that the whole surface area of the pin is at base temperature. If it is base temperature, the temperature difference will be high. Okay, so the entire fin will be at its root temperature only when the material of the fin has infinite thermal conductivity. So here we can see the formula. So it is the ratio of actual heat transfer by maximum possible heat transfer, that is the efficiency. So efficiency formula is equal to, so Q actual by Q maximum possible heat transfer, that is the formula. So here just like I'm taking the two types of fins. So one is the long fin, another one is the insulated end fin. So efficiency of the long fins, that is the Q actual by Q maximum possible. It means the rate of heat transfer of the actual long fin and maximum possible heat transfer. So we'll see that one. So you already rate of heat transfer for the long fin, we already derived that one. That is the formula is equal to, so under root of HPKA into T naught minus T infinity. We already derived this one. Okay, so it means under root of HPKA into theta naught. Theta naught is nothing but T naught minus T infinity. Okay, so this is the actual heat transfer for the long fin. For the long fin here, AC, it means area of the cross section. Here it means you can observe like this one. So this is the area AC. AC. So here AC is nothing but cross sectional area is nothing but width into thickness. So this is thickness. That area. So how to mention? So take this one. So this AC is the W into T for the rectangular body. If it is just like circular objects, it means this area is the 5/4 d square. That is the area. But in case of maximum possible heat transfer means, so maximum possible heat transfer means, so just like by using this diagram, I'm refer this diagram. So the total surface area, okay, so top surface, bottom surface, side edge surfaces. So the the temp through that area, the heat will be dissipated through convection mode. So that is Q is equal to H A and delta T, maximum temperature difference with T naught minus T infinity. So here H is the rate of heat transfer. You know that for the atmospheric air. So area is the effective area. Here effective area is just total air, top surface area of the fin, bottom surface of the fin, and the side edges of the fins. So we can measure that one. Area is equal to perimeter of this one P into length, total length, that is equal to L. So P into L. So here area, so convection related area. So you have to remember this one. So there are two types of the areas, you have to identify this one. Okay, so this area, end area, cross sectional area, this area, so total area of the fin. So to further to pass the convection or to proceed the convection process here, a fin, it means convection heat transfer area of the fin. Convection heat transfer area of the fin. So that is the, so mm, perimeter into length. Okay, so it means how to understand that one. So this is the fin. Okay, so this is the just like base surface. So in this one, end area, this is the cross sectional area, that is AC, W into T. So width is equal to W, T is the thickness. So this area of the fin means, so total surface area, top surface area, bottom surface area, side surfaces areas. That means, so perimeter. So this is the perimeter. This is the perimeter. So it means P is equal to 2 into W plus T. So this perimeter up to length L. So that is the total surface area, lateral surface area will be counted. So that is the A fin. So we have to identify that one. So this A fin is equal to perimeter into length. Okay, so if you apply this one, so here you can understand that one. So theta naught minus T infinity, T naught minus T infinity, T naught minus T infinity will be cancelled. So here also, so this one under root of HPKA divided by HA. A is equal to here perimeter into length into perimeter into length. So okay, here just like here HP under root, here HP is without root. So then that value is equal to, will be like this one, under root of, so KA remaining term. So here KA. So here HP under root. So L is the remaining term. So that is, you can write 1 by L. Okay. So 1 by L into under root of KA by HP. So KA by HP. So that is the value. Okay, you know that M is equal to under root of HP by KA. Just reverse. Then this value is equal to 1 by M. Okay. Then final value is equal to L into M. It means 1 by ML. So 1 by ML is the just efficiency of the long fin. That is the formula for the efficiency of the long fin. You know that M is equal to under root of HP by K. Okay. So similarly, we can write like this one, efficiency of the insulated tip. Insulated tip. So Q actual by maximum possible heat transfer. So maximum possible, here also same, here also same. HA pin into T naught minus T infinity. So Q actual you already derived in previous slides. So that is under root of HP KA into theta naught into tan HML. So that is the formula already derived this one. So same here. This is the same term similar to previous one. Here theta naught is equal to T naught minus T infinity. Same. So it means, so this total term we already got that one 1 by ml. So remaining is the tan h ml. Okay. So finally, so this is the formula. So tan h ml by ml. So efficiency of the insulated tip is equal to tan h ml by ml. So you have to remember these two formulas. So efficiency of the long fin is equal to 1 by ml. Efficiency of the insulated tip, so that is the short pin, you can write like this one, short pin is equal to tan h ml by ml. Okay. Now we will see the effectiveness. So already we learn about the efficiency in previous slides. Now we will see the effectiveness. So effectiveness will be compared. Uh, so before So comparing of presence of the fin or lack of fins, just like. So if you add the pin, so what is the effectiveness? If there is no pin attachment, what is the effectiveness? We'll see that one. So the pins are employed or used to increase the rate of heat transfer. The main object of the pin is to enhance the heat transfer rate. Okay, because if you add the pin to the base surface, automatically effective area will be increases. If the effective area increases, automatically rate of heat transfer will be increases, because q is directly proportional to area. You know that one. Okay, so this is the just like main function of the main application or main intention of intended purpose of the pin. So you know that. Okay, so in the absence of the fins, if the fins are not attached, okay, the heat convected by the base area, the heat convected by the base area is given as HA T naught minus T infinity. HA T naught minus T infinity. So it means, so suppose this is the base area. So one pin is circular pin is attached. Okay, attached here. So if you just like this fin covers this small elemental area, this area. So this area is increased by this total area. Okay, if you remove this pin here, just like this is the area how to consider this one. Okay, so in the absence of the pin, the heat convected by the base area is given. So it means heat convected so by the base area is only through this one. Okay, so if you add the fin, so this small elemental area will be increased like this one. Okay, so just like, so we'll see that one. When the fins are present, heat transfer by fin qf can be calculated by the just like above equation. So take, you will see the uh, so ratios for the effectiveness. Effectiveness is represented by epsilon. So effectiveness for the long fin, so you know that. So effectiveness for the long fin is equal to, so q actual fin, so same actual fin or q fin, rate of heat transfer in the specified fin for the long fin, or q without fin. If you remove the fin, what will happen? Okay, so q actual for the long fin, that is the formula you already derived that one, under root of hp ka into theta naught t naught minus t infinity. So this is the formula. Okay, by, so q without fin, if you remove the fin, so what is the rate of heat transfer? So if you suppose this is the base area, just like we are adding some rectangular or fin or circular fins, just like here adding circular fin. So this is the rectangular fin. If you observe this side view, just like this is the main surface, so only rectangular surface pin is attached like this one. It means this small elemental area of the base area is enhanced by the total area. Okay, if you remove this fin, this only heat dissipation by the small elemental area. So because this place only occupied by the fin. So here just like we have to observe that one, q fin means ha theta naught. Ha theta naught means so h a into t naught minus t infinity. Okay, this area is nothing but this small covering area. So this area is nothing but, here covering area is nothing but edge area. So end area. So this end area is equal to w into t for the rectangular. So same for the circular, 5/4 d square. Okay, so in efficiency, that is different. In effectiveness only, so what area is covered by the uh, pin, you have to consider that one. So covering area means area of the end area of the pin. So that is the, so that area is equal to 5/4 d square. So here under root HPKA, this area also same end area of the fin. So it means so AC, ER, both areas are same. Okay. So you have to remember that one. So both areas are same. Then the formula will be like this. So under root HPKA into theta naught divided by so HA theta naught will be cancelled. HA. So here under root HA, here under root, so without root. So it means so remaining terms is equal to PK by HA under root. So this is the PK by or KP by HA. So this is the formula under root of KP by HA. K is the thermal conductivity, P is the perimeter, H is the area, and H is the rate of heat transfer, and A is the area. So area of the cross sectional end area. Okay, total not that top surface or bottom surface, not that of areas. This is the attaching area, end area. Just okay, you have to remember that. So similarly, just like effectiveness of the insulation, insulated tip, it means short pin. So is equal to that one also is equal to Q fin by Q without fin. Q fin. So without fin means so what area is attaching areas occupied by the fin. So that area how to consider that one. So just like one. So this is the base area, this is the end area. So if you observe the from side area, so this occupied area, that is the nothing but so end surface area, end cross section area of the fin. Okay, same. So if you observe, just like if you substitute that one, rate of heat transfer for the uh, actual uh, actual rate of heat transfer for the short pin, that is the formula under root of HPKA into theta naught into tan H ml by so Q without fin, so HA into theta naught into T. So this is HA. A area is the cross sectional area, end area of the fin. So or starting area of the fin, which is attached to the surface. So this AC and area AR both are same. Then the formula will be like this. So tan HML into under root KP by HA. So KP by HA. So here only KP by HA, here tan HML into KP by HA. So AR is the area at the root equivalent to cross-sectional area of the fin. So end area or starting area, which is attached to the base area. So these are the just like efficiency and effectiveness of the fins. Both are very important to evaluate the performance of the fin. Okay, now we'll see the some few notes, some points. Okay, the effectiveness. So the formula effectiveness is equal to so Q fin by Q without fin. Okay, rate of heat transfer when the fin is attached, the rate of heat transfer to the base without fin. So when fin is not attached, so that is the formula. So epsilon, if the epsilon is equal to 1, epsilon is equal to 1 means so Q fin is equal to Q without fin. It means the rate of heat transfer when the fin is added. Here rate of heat transfer without the fin. So both are same means there is no influence of the fin. So fin does not affect the heat transfer rate. So at all. So if it means effectiveness epsilon is equal to 1 means there is no use of the fin. So fin is not affecting to enhance the rate of heat transfer. You have to remember that. So next condition 2. Suppose effectiveness is less than 1. Less than 1 means it means less than 1 means so Q fin is less than Q without fin. It means so rate of heat transfer when the fin is added is less than the rate of heat transfer without fin. It means the fin is acting as an insulating material, because by adding the fin, automatically rate of heat transfer is decreasing. So without fin of the rate of heat transfer, it means fin act as a insulation. So it means instead of increase the heat transfer, it is decreasing. So it means that is the insulating property. Okay, fin act as insulation. So that is the condition 2. So third condition, it is a required condition, that is the effectiveness is greater than 1. Q without effectiveness is greater than 1 means, it means Q fin is greater than Q without fin. Without fin. It means so rate of heat transfer when the fin is added is increased, is greater than rate of heat transfer without fin. So that is the, it means fin act as a properly, acts properly. It means that the heat transfer will be increased, means fin effectively act working. You can uh, so assume that one. So these are the three conditions to explain the concept of effectiveness of the fin. Okay, so here also some relations also given, then you can identify it. So effectiveness of the fin is directly proportional to 1 by h. So already derived that one. Here you can see, so effectiveness is equal to under root kp by ha, kp by ha, under root kp by h, under root kp by ha, effectiveness. Okay, it means so if the thermal conductivity increases, effectiveness will be increases. Effectiveness of the fin is directly proportional to under root k. If the thermal conductivity increases, effectiveness of the fin increases. So next, if the perimeter increases, it means you can perimeter and cross sectional area relations. So effectiveness of the fin is directly proportional to P by AC. It means so perimeter should be uh, greater than the cross sectional area and cross sectional area of the pin. So just like this is the pin. Okay. So this total cross sectional perimeter, this perimeter, it means so this area or otherwise this perimeter. This perimeter P should be greater than the, so W into T. So area of the end area of the cross sectional area of the pin. If that is the condition, automatically so effectiveness will be increases. So epsilon is directly proportional to, so under root of P by AC. Next to, so effectiveness is indirectly proportional to under root H. If the rate of heat transfer increases, effectiveness will be decreases. The rate of heat transfer, coefficient of the heat transfer coefficient of the air will be decreases. If they decreases, automatically effectiveness increases. These relationships also you have to remember this one. Okay, so these are the concepts of just like efficiency and effectiveness of the fins. Okay, totally we derived the uh, so rate of heat transfer for the three types of pins. One is the long pin, another one is a short pin or insulated end pin. Next to convection of the end pin. These are the three types of the pins. We derived the rate of heat transfer for the three pins, and we already discussed the effectiveness and efficiency of the pins performance of the pins. So performance evaluation is done by efficiency method and effectiveness method. We already derived those formulas for the this one. Okay, so these are the few points, just I am highlighting this one. This one, remember this one. So pins are generally used when convection heat transfer coefficient values are rarely low. Okay, to enhance the convection heat transfer rate, so we'll add the pins, because it's mainly used, these are used for the just air cooling systems. Okay, when air or gas is the medium, heat transfer is by convection takes place, because the convection means the rate of heat transfer takes place from the solid to liquid or fluid to fluid. Okay, fin material should be made of highly uh, conductive materials. Okay, so aluminum is preferred material, that is the low cost and uh, just weight resistance to corrosion. That is the good material. That. Next, to lateral surface area. So that is the already discussed. This one, Py cross section area of the fin should be high as possible. We have to take care of these points to prepare that to design the uh, pins. So fins with parabolic and triangular profiles. So this contains less material and good surface area. So are more efficient for the minimization of weight and maximization of the area. Automatically, these are enhances the rate of heat transfer. So the efficiency of the most fins are used to practice. So 90% of the heat transfer rate will be increases by the help of the fins. So uh, the details about the fins are very useful for the enhancement of the heat transfer. So we'll see. Now we'll see one numerical which is based upon long fin, just like a short pin. Okay, so okay, here very long pin. So the condition is very long pin. So first pin. So diameter of the long pin is given 25 mm, convert into meters, 0.025 meters. Thermal conductivity also K is equal to 380 watt per meter Kelvin is given. So extended temperature T naught also given 120 degrees Celsius, and T ambient also given 25 degrees Celsius. Okay. So heat transfer coefficient, so H also given, that is the 10 watt per meter Kelvin. Okay, meter square Kelvin. So calculate the heat loss for the long fin. So already got that formula, Q is equal to under root of HP Ka into theta naught. Okay, it means HP Ka theta naught is nothing but T naught minus T. Okay, that H is given. So perimeter P is equal to 5/4 perimeter pi d. Okay, so pi d. So diameter is given, then you can find out the pi d, and the area of the cross sectional 5/4 d square. So d is given, you can find out the area, and K thermal conductivity also given directly. Then you can substitute these values and you will get the rate of heat transfer. This is a simple formula, so you can solve so many problems based upon these three pins. Okay, thank you for watching this class. So remaining topic will be discussed in next class. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.